we're not going to have anything to do with geomechanics per se. It's really just sort of, if anything, an advertisement for the course I'm going to teach next year. And I actually found out yesterday officially I'm going to teach it in the spring. So it will be not this spring, not in a month, a year from now. I'm going to teach a course. The title of the course is like Advanced Computational Methods. It's going to be a graduate course, but it's going to be a parallel computing class, essentially. I know some of you may not be here by then. And I have some resources I can share with you. If anything I talk about today is interesting to you, I have some resources I'll share with you. But, you know, basically, you may have already encountered this in your studies, but eventually you're going to get to the point where you want to solve problems that are too big to solve on your laptop or even a powerful desktop. And so we have access here to world-class supercomputer, right? But of course we can't just because you have 68,000 processors, it doesn't mean that you just send your code over there and you get 68,000 times speed up, right? You have to write your code correctly. And you know, the most ubiquitous form of that is distributed memory parallelization. So usually the reason our problems are too big, I mean, the reason our codes are slow is because our number of unknowns, our domain is too large, right? Number of unknowns are too big. And so if you have some giant domain, and when I say domain, you know, think reservoir, right? So if some giant reservoir, then, you know, I want to break this thing up into pieces to be solved by other, you know, so basically sometimes we'll have so many unknowns that the domain won't even fit in the memory of a single node on a computer, right? So we resort to distributed memory parallelization, where we're going to break this thing up and send this off to 4 processors, for example, right? And then send that off. Of course, to solve this thing, these aren't, you know, so this is going to be worked on by one processor and that and that and that. Of course, they're not mutually exclusive, right? They have to have continuity across here, continuity if we're talking about displacements or, you know, and so there's always some sort of what we call ghosted regions, which are shared by multiple processors, and then there's communication across a network, okay? And that communication occurs in a supercomputer like at TAC via InfiniBand, which is like, you know, gigabit per second speed. So it's not gigabit, like 10 gigabit per second speed. It's fast. You know, it's not like your network connection. So it's really, really fast. And the most ubiquitous sort of programming interface that we use for this type of programming is called MPI, message passing interface, right? And so it's a standard API which has become the standard for parallel computing. Now, I'm not really going to talk about shared memory parallelization, but so on each of these processors, so really, you know, 0, 1, 2, 3, what I'm calling a processor really more specifically would be like a node or a blade in a supercomputer. And each of these may have their own multi-cores. Right now, all of our chips are essentially multi-core. And so each of these may have some multi-core on a shared memory, right? When I talk about memory, I'm talking about the RAM associated with this processor, right? So this machine can't access that one's RAM except by communicating information. But if I have multiple processors on a single machine, they all access the same RAM. And there are certain APIs for taking advantage of that type of parallelization too, namely OpenMP, OpenACC, other things like that, threading, thread building blocks, pthreads. So there's several APIs which can take advantage here. But ultimately, the sort of what the gain we can get from that is fairly limited at this point. Really today, the standard procedure is distributed memory parallelization. So break our problem up, send it out to a bunch of nodes, and try to solve it. So let's see how many I have. Let's see what. I think I turned it off, so it's going to take a second to come back on.